Welcome to today's webcast, Modular Open Systems and How the MOSA Approach is Helping OpenVPX Evolve, brought to you by Military and Aerospace Electronics Online. I'm John Keller, Chief Editor of Military and Aerospace Electronics. Today's event is sponsored by Elma Electronic in Fremont, California, Interface Concept in Quimper, France, and Concurrent Technologies in Woburn, Massachusetts. This presentation centers on the Modular Open Systems Approach, or MOSA, and how it can help drive design and technology trends and open system standards, such as VITA's OpenVPX specification. MOSA, formerly known as Open Systems Architecture or Open Systems Approach, is a method to assess and implement technologies based on open modular computing design elements. This program will present goals of MOSA, technology trends and the impact of MOSA on OpenVPX, and the kinds of network systems and processor capabilities that MOSA requires. Our presenters today are Ken Grobe, Director of Embedded Architectures at Elma, Nigel Forrester, Director of Business Development at Concurrent Technologies, and Frank Lefebvre, Sales Manager at Interface Concept. This presentation is live and interactive, so you can submit questions at any time by clicking on the Ask a Question button in the presentation window. After our presenters finish, I'll open it up to questions from our online audience and for discussion among the panelists. First, a couple of housekeeping details. If you're running pop-up blocking software such as the Google Toolbar, you will need to disable it to view this webcast. In addition, we recommend that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It also will be accessible from the homepage at www.militaryaerospace.com. So, let's get started with Ken Grobe, Director of Embedded Architectures at Elma. Ken?
Thanks, John. So hi, this is Ken Grobe with Elma. I'm here today to talk about trends in packaging and infrastructure for DoD modular systems and the impacts we see with that driving OpenVPX. So if we look over time, packaging standards have been driven by VITA and PICMIG, two standards bodies, for using Eurocard modules for decades. And recently, with the DoD introducing the Modular Open Systems Approach, this approach is driving systems capabilities to improve capabilities, availability, and how fast it takes to implement the systems, compatibility of the technology and the modules and products being used to implement the systems, and costs. So this effort has led to some other standards to actually affect it. So if we look around the landscape in the industry, we see several standards. One from the Army called CMOS, which stands for C4ISR EW, Modular Open Suite of Standards, a real mouthful. So CMOS is a better way to say all that, but this addressing the C4ISR and EW space. In the Navy, they have a standard called HOST, or Hardware Open Systems Technologies, and then in the Air Force, a standard called Sensor Open System Architecture. So other initiatives that have been going on around those include Future Airborne Compatibility Environment, which has been ongoing for nearly 10 years. One called MORA for Modular Open Radio Frequency Architecture. So these are substandards which would fall under the standard umbrella of CMOS and then hence some of the others. And also something called VICTORY, Vehicular Integration for C4ISR Interoperability. So a communications standard, if you will. So one of the things all these standards need is a hardware platform or a hardware base, if you will. And SOSA, CMOS, and host have in fact chosen OpenVPX to be the base hardware standard. So what is, from our view in the packaging industry and the modular industry, what are we seeing MOSA's objectives? MOSA at the top is a collaboration between government and industry through the other standards bodies that we discussed. So some of the objectives that we see MOSA involved in would be specifying base system architectures. Here we see this happening in the SOSA standard. As I mentioned before, a need to select a hardware standard to base the systems upon, and this has been chosen as OpenVPX. And another central goal is to promote interoperability, thus compatibility through the definition of modules, and this is being done through constrained module profiles, and we'll show you what that means in a little bit. System management, which has been around in other communication standards like, let's say, telecommunications, advanced TCA, or compact PCI. Now it's being made a required component of a VITA system, or now a MOSA-based system, which is being done through a standard called VITA 46.11. Another point would be to modularize, or to normalize rather, the module power. So the power modules or power supplies that are being used amongst the modules to make that consistent. And lastly, as things evolve, computational capability increases, we see power increasing. And while power increases, it requires us to look at new ways to cool our systems, and we're seeing new cooling techniques being prompted by this modular work. So how we interconnect things are driven by, in OpenVPX, through something called a slot and a module profile. And this is a collection of slot and module profiles that are being proposed or driven by the SOSA standard. And SOSA has become the umbrella standard for both CMOS and host. So you can think of them all rolled together, where SOSA is sort of the lead or the umbrella. And underneath that, this SOSA standard, now released in Snapshot 2, has specified these specific profiles as being sort of the go-to profiles for switches, payload modules, CPUs, and also I/O interfaces. So what's happening with the profiles is that they're becoming constrained, or let's say more well-defined, and by doing this, it makes the profile describe the module in its entirety. This way, if a manufacturer builds a single board computer, like Nigel will explain in the following talk, one would see a computer that can be built by more than one manufacturer and can operate consistently. Same thing with Ethernet switches and payloads. So it's been described as eliminating the white space in the profile, where if you look at this profile, you see white space, which means it can be defined as anything. This is being defined for specific user I/O. In the other cases where we see them colored in or filled in, they're being specifically defined as you see, and they can't vary, so one needs to build it in a certain way. So when we speak about infrastructure, as we look at the system architecture, we see the systems being built with network infrastructure that requires high-speed switches, timing capabilities where the architectures allow clocks, if you will, to provide timing reference within the architecture. And this timing has resulted in a module and a slot that defines precision navigation and timing, so there's a specific capability This would include GPS capabilities. Another part of the infrastructure would be system management, as we mentioned, which provides chassis management, which is monitoring things like power and health and communications between the modules at a low level. And then power systems, defining a standard way to implement power. This here with Vita 62. So if we look at trends and what's driving us now when we're looking at infrastructure for packaging and backplanes, and also the architecture and capabilities of certain modules, we see on the left this green block which describes Ethernet speeds. We see link speed on the far left on the axis, looking at 100 megabit, gigabit, 10 gigabit, 40, and now 100 gigabit capability. So over time, there's been many years between 10 and 100 megabit. If you look at it from somewhere in the mid-1980s through mid-1995. But over time, this speed increase has been taking less time to increase. And now we're at the precipice in embedded systems of 100 gigabit Ethernet capability, with other standards that have been recently introduced that include 2.5, 5, and 25 gigabit Ethernet. On the PCIe side, where we would look at data transfer in systems, we see PCIe changing from 2006 at 5 gigatransfers a second to 10 giga to, in 2010, 8 gigatransfers per second, and now in 2017 moving to 16 gigatransfers a second. What this is doing is driving the need for higher speed channels in our backplanes. So we're driving the signaling rates from 10 gigabits up to 25 gigabits per lane. And this 25 gigabaud, when it's looked at the symbol rate and encoded, supports 100 gigabit Ethernet via 4 backplane lanes. And this is how one would make that in a copper backplane. So what are the challenges? We're faced now in packaging to be able to build a backplane that operates 2.5 times faster than the 10 gigabit, which is currently what we would designate a high-speed backplane. And this is driving the need for better signal integrity modeling and rigorous modeling and simulations to be able to prepare a design that will function when we build it. It also drives new materials, high-speed materials with better insertion loss, better capabilities, and materials that we've recently used to be materials like Megtron 6 or Isola 408. Now we're moving to Megtron 7, and the materials cost more as we go down the road. And the other thing that this is driving is in VPX, we have a connector that looks like the one you see on the bottom left. This drives a new type of connector because we're currently speed constrained with the RT2 connector. So companies like Tyco have developed a connector called the RT3, which allows us to be able to operate at the channel speeds that we need to support the new 2.5 times speed backplanes. So if we look at certain go-to profiles that describe our infrastructure, these profiles are being shown that highlight useful network switch profiles in 3UVPX. And these profiles are defined today to provide 10 and 40 gigabit capability on these yellow fat pipes and 1 and 10 gig capability on the green ultra-thin pipes in a dual domain switch. So this gives us the capability to provide Ethernet infrastructure within the backplane across modules, so all modules can be connected via Ethernet, and provides us a unique data plane and control plane capability. We also see the inclusion of fiber optics in the bottom through this 67.3D connector that's included in the second profile, so a similar switch but with optical capabilities. So the optical can be used in between modules or it can be used to take I/O out of the system. And then lastly, for hybrid solutions where we need Ethernet and PCIe, one can see a hybrid switch profile that provides fat pipes and ultra-thin pipes in one switch of both Ethernet in the green and PCIe in the yellow or the gold. So as the MOSA work takes place through the substandards, where we pointed out SOSA was the lead standard. In so doing, new profiles are being suggested, and it's causing change. So we see in 6UVPX for switches, we have a Vita profile now where the control planes on the top and the data planes are on the bottom. And we see in the SOSA profile, it's causing that to be inverted. So that drives change to the module vendor, and the module vendor needs to make now new implementations that fit the new profile going forward to align with the standard and provide compatible implementation. And this module, you see white space going away at the bottom and fiber optics being included in the definition. So we mentioned power and cooling and how that is evolving. What we've seen over the years is in OpenVPX, we have a standard for air-cooled 48.1 and conduction-cooled 48.2. We see new standards now where we're using an approach called air flow-through cooling, which drives air through the module, right through the heatsink here on the side, and it allows the module to dissipate higher powers and actually be cooled with this new technique. So this technique addresses modules from 60 to 130 watts or higher, and it requires the mechanics to change relative to how the card guides are being built and the way that the module is actually fabricated in its pitch. So here we have a wider pitch module that allows for the cooling fins inside it to allow air to blow up through the module and then out through the top. Likewise, this can also be done with liquid, and there's another standard called Vita 48.4 that provides for a liquid flow through cooling capability, which can dissipate even greater amounts of power. So another set of changes required, and this has now been standardized by Vita, and these things are actually being built. So when we look at connectors, we see a trend to move from copper to fiber, and we also have the need for high-speed RF signals, analog, to be connected and addressed in our modules. This requires high-density RF connectors, as you see in the top right, where we have tiny RF contacts that allow the modules to pass a mated RF signal through from the board into the backplane. Likewise, we also have the need to send fiber optics through the board and into the backplane, and there's a MT furl, which is this little black rectangular piece here inside the connector, which allows us to handle multiple fibers and to be able to connect it. Now, today we can connect somewhere between 12 and 24 fibers through this self-aligning connector. And then further, we need to put our transceivers somewhere on the board, and there are new transceiver technologies being developed that allow the transceiver to actually be embedded into the connector so we don't have to have another ribbon on the board, and it can be directly passed through the module and into the backplane. Lastly, as power systems evolve, we see the need for compatibility of the power supplies, and the new standards are driving 12 volts only with 3.3 aux versus the conventional scheme where we had 3.3, 5, and 12 in the power supplies to normalize them. This way, one would make a 12-volt rail, say, be able to supply 60, 70, 80 amps or whatever it's going to be, and then 3.3. So you would have less variables relative to how the power supply is actually constructed. Further, these power supplies are also becoming intelligent with system management, so we see Vita 46.11 being implemented on the power supply. So there's a chassis manager to actually communicate with the supplies to look at their outputs and to provide some level of control over the supplies themselves. So this is leading us to the chassis manager, and these are examples of what a chassis manager mezzanine looks like in the system management hierarchy. It uses a serial interface called IPMB, and this shows a card that's made by Elma that implements chassis management in a system. So, in summary, new technologies and standards are driving many impacts on chassis, backplane, and power system design. So we're now faced with backplanes that will operate at 25 gig a baud and beyond, networks that will use 100 gigabit 3U and 6U Ethernet switches, moving up from 40 gigabits, and then PCI interfaces moving from 8 gigatransfers in Gen 3 to 16 gigatransfers in Gen 4. Chassis will use new cooling techniques, continue to use conduction in Beta 48.2, but we'll see new techniques, air flow through and liquid throw through, using 48.8 and 48.4. And the power supply is evolving, and VITA still supporting the older supply techniques with multiple channels, but allowing and favoring the techniques for plus 12 volt and 3.3 volt supplies. We'll continue to see fiber optics evolve and be used more readily for I/O in the chassis, but we'll also see modules being connected together with fiber optics for higher speed. And this will occur as we move beyond 25 gigs and going from 25 higher up to rates of 100 and 200. And then lastly, we're now making reference designs. These are new backplanes and system architectures that provide chassis and backplane references for new modules to be able to be plugged into to prove out this new capability and to provide ways for the industry to be able to do interrupts and demonstrations of the technology as we move the technology into the mainstream. So that's what I have for you today. I'll hand it back over to John.
Okay, thank you, Ken. Now we'll turn it over to Nigel Forrester, Director of Business Development at Concurrent Technologies. Nigel?
Thank you very much, John. And hello, everyone. So for the next few minutes, I'm going to concentrate on some of the advantages that will hopefully make VPX processor boards easier to adopt and use. I've used 3U boards as examples, mainly because they have fewer connections and they're a bit simpler. But the same principles extend exactly to 6U boards. And as you may have already guessed, Concurrent Technologies' main focus is on developing and manufacturing Intel processor-based boards for these type of critical embedded applications. So some people might say that after more than 30 years of processor board design, we'd be experts. But one of the suggestions we're adopting with this MOSA approach is radically different to the way we've done things in the past. So I guess you could say there's always a different perspective and something new to learn. So I'm sure many of you who are on the call are already VPX experts. But for anyone new to VPX, this is a top-down view of a typical 3U VPX Intel processor board. And just very quickly, the yellowish sections at the top and the bottom, they slide into the guide rails for air core deployments, but they're snapped off for conduction core deployments to make room for the heat frame that contains the wedge locks. They in turn make a thermal interface to the chassis in this area. This particular board also has an XMC site. You can see there's two XMC connectors near the sort of right-hand side of the board there. And that's for an expansion mezzanine. And unfortunately, to be strictly compliant with the specification, that requires that there's no components fitted in the board area near the front panel. So that leaves a surprisingly small area for components. And so this type of board is actually surprisingly difficult or challenging to design, but I guess that's where our expertise comes in. The main reason to show the picture is for the connectors. So if you look at the top right-hand corner, the P0 connector on a 3U VPX board contains the power and some basic system signals like sys reset. The P1 connector also has some system signals, plus the main interconnect fabrics that Ken touched on. They're referred to as control data and expansion planes in VPX terminology. And then the P2 connector at the bottom Can also sometimes be used for expansion plane fabrics, but mainly is used for user-defined I/O, as per the example I've got on this slide here. So one of the cool things really about the OpenVPX standard is that the connectors are shown visually in the standard, and Ken actually showed some of these types of diagrams in his presentation. And this particular example is of a very common, what's called a slot profile. This one's usually called the 2F2U profile. But if I'm strictly correct to the OpenVPX standard, this is a slot profile on a 3U VPX backplane. So that's what the SLT3 bit in the top left-hand corner means. It's a payload board, which is a -PAY, and it has two fat pipes for the data plane and two ultra-thin pipes for the control plane. So again, the data plane, a fat pipe is effectively a by-4 differential link, and an ultra-thin pipe is capable of a by-1 differential link. And then the last part of the specification there, the -14.2.3, refers to the exact section of the specification. So you can easily find out more information about these or refer back to the specification. And in this case, as you probably know, the defining body for the OpenVPX standard is the VITA standards body. So you can find more information on their website at vita.com. So two other things to note. Firstly, on each row of the VPX connector, there are pins suitable for single-ended and differential signals. So they're shown diagrammatically. And secondly, in this particular profile and many others, many P1 and all P2 pins are reserved for user-defined I/O. And for each of the slot profiles in VPX land, like the one I just showed, they're capable of accommodating boards with different module profiles. There's a bit of an eye chart here, but this is a list of the module profiles for that previous slot profile board. And so again, for example, we commonly supply processor boards based on the -10 module profile out of this list, which is the penultimate one, with PCIe Gen 3 data plane connection and 1000 base BX control plane connection. But other system level configurations with rapid I/O or 10 gig Ethernet data plane connections are possible. And so these profiles, or module profiles and slot profiles, are now defined in a separate Vita 65.1 document so that they can be updated without the need to change the underlying base Vita 65.0 OpenVPX standard. And I've got the reference for the exact document at the bottom of the slide there. So having defined the slots and the module profiles for a system configuration, an architect also needs to define the right connections are made between each slot on the backplane. And in this example, it's quite a simple one. There are 5 payload slots and a switch slot. The control and data plane connections from every slot are connected to a single switch, but there are much more complex configurations. In fact, Elma have a 12-slot SERDEC backplane, which is a good example of a much more complex scenario. And as well as internal connectivity, the switch can provide external network connections. And Frank from Interface Concept will talk about the things they're doing in this space shortly. So getting back to the user-defined I/O, these signals from the P1 and P2 connectors on the front board, the main board, are typically tracked directly through the backplane to a rear transition module, which is also called an RTM, if you're using perhaps a development system or you've got an air-cooled deployment. And these RTMs are usually simple passive connector modules. They're relatively easy to create and modify, and historically we created a new one for each processor board to add functionality as new interfaces became available. So these RTMs use standard connectors. They're easy to use. However, in rugged conduction cooled systems like this ATR box type box from Elma, they don't have the ability to use an RTM even for development. So the user I/O signals from each payload board are usually tracked along the backplane to an end slot. And then this slot is then populated with a special connector board that sits just behind the front panel and contains the military-grade connectors, like the ones shown. And because there hasn't been any standardization of the user-defined I/O, every vendor has chosen a pattern that suits their particular requirements. Slightly embarrassingly, the two examples shown are a subset of the P1 connector pinout for two of our recent Concurrent Technologies processor boards. And if you look at the orange SATA pins, they're in completely different places on the connector. So there's a good reason behind that, but what it does is it prevents the ability to interchange processor boards in these rugged systems. And in practice, that's led to a design of a plethora of VPX backplanes. And as Ken was saying, this isn't really sustainable in the future due to the increase in signal speed and backplane complexity. So, what's happened to sort of change this situation? Well, one of the things that Ken mentioned was the SOSA consortium. They've made a recommendation to the VETA community that in turn is driving an update to the OpenVPX profile specification, VETA 65.1. So there are several different suggestions depending on the module type, but for processor boards, the two most significant are the reduction and removal of user-defined I/O and the commitment to use plus 12 volt for power. So first, let's concentrate on the profiles. And I've got a view here of the proposed or primary and secondary profiles for processor boards. Again, sorry, it's a bit of an eye chart, so we'll look in this into a bit more detail going forward. But if you just can see the bottom section of the middle and the rightmost diagram, you can see they're coloured grey. And what that means is that there's actually no P2 or a reduced size P2 connector on the processor board. And this is so that a processor card can be fitted in the same backplane slot as an FPGA card, where this section of the backplane is populated with those optical or coaxial connectors that Ken had on one of his slides. So they'd be used for a direct connection of RF signals to an FPGA board, but obviously wouldn't be used in a Intel CPU board. So if we look at the I/O intensive profile first, which was the one on the left-hand side, so this is hopefully a bit more readable. There are some pins or I/O pins for things like video, USB, etc. But whereas they were coloured white and undefined on the previous version of the specification, here you can see that they are tightly defined. There's also the expectation here that the data plane will typically be 40 gig base KR4 Ethernet with PCI Express based expansion plane used for connectivity between pairs of processor and GPU or a processor and FPGA cards. So if an application needs extra I/O, the thinking is that this will be provided by an XMC module, and there are additional proposals around the XMC pinouts. There is one product that's been on the market for a few months based on this profile for another vendor, and that has a 40 gig Ethernet data plane connection as expected to be typical. So similar to the slot profiles, there are a number of possible module profiles with using these this profile. So here you can see that just about make out the data expansion and control plane options. But also on the right-hand side of the chart, hopefully you can make out that for the first time, we're actually defining the expected I/O implementations. So there's video, USB, storage, and so on there. And the current storage protocol there is based on SATA, but my expectation, and also it was covered on the previous slide, is that over time we'll also see some additional module profiles that include PCIe for NVMe-based storage. So if we switch gears to look at the composed compute-intensive slot profile, this is very interesting because there's no user I/O other than the maintenance ports for initial board bring-up and maintenance. So it's anticipated that these boards will be dedicated to computational activity, and therefore all the remaining connections are utilized by the control, data, and expansion plane connections. The dash number in this slot profile specifies whether the P2 aperture is empty or fitted one of those optical or coaxial connectors that we talked about a minute ago. And then if I look at the module profiles for the compute-intensive processor slot profile, you can see there's a real convergence here around 10 or 40 gig Ethernet on the data plane. And there's options for either PCIe or Aurora for the expansion plane connectivity for either processor boards or FPGA boards respectively. These options have been chosen to enable multi-processor-based server configurations with high-speed Ethernet connectivity between multiple slots at the same time as high-speed point-to-point connectivity between adjacent slots. So very analogous to rack mount server type installations where you have lots of Ethernet cables, perhaps 10 gig or 40 gig Ethernet connections up to the top of the rack switch. But in that case, you'd have a direct connection for a GPU board, perhaps on each rack mount server itself. So it's squeezing the same sort of thing, but into a much more rugged, smaller environment, VPX environment. So to coincide with the webinar, we're announcing our first compute-intensive processor board today. This is based on a 12-core Intel Xeon processor. It's got 64 gig of DDR4 DRAM and 1 terabyte of storage. And with all processor boards standardizing on using a single 12-volt supply, this is going to simplify the requirements for power supply vendors. So they should be able to offer now a range of standard power supplies rather than having to customize each supply to match the amount of plus 12, plus 5, and plus 12 volt current requirements for the individual payloads in a system. So this product will be available as a rugged conduction cooled module. And as you can see from the block diagram, we're enabling an optional front video and USB connection on this board for initial setup purposes. That's a bit of bells and braces really, but it makes it life easier, at least initially. And we're also enabling variants with options of data control on expansion planes to help with some security requirements. So you can find more information on this product on our website or by contacting us at Concurrent Technologies. Hopefully I've given you some interesting things to think about, and with that I'd like to turn it back to John.
Okay, thank you, Nigel. Now let's hear from Frank Lefebvre, Sales Manager at Interface Concept. Frank?
Hello, John. Thank you. Thank you, Nigel. Thank you, Ken. So you give a good overview about the VPX standard and how the VPX standard is defining the backplanes and the payload. Now I would like to introduce to you how the VPX standard is defining the Ethernet switch. And what is interesting to see is while until some time ago, the Ethernet switch was the last bricks the integrator were looking for their system. With the VPX standard expansion and more recently the SOSA standard expansion, the switch is now seen as a part of the system foundation. But today the standard is defining a couple of profiles for the switch, and with this presentation I will try to show how we can cover most of the requirement of this standard. So the embedded switch market is not really driven by the board and board developer and vendors. It is driven actually by the standard and the semiconductor market evolution. And I will try to give you some examples of VPX switch that are aligned with the MOSA standard. In the same time, the embedded switch market is also driven by the requirement and at the end the customer agility to switch from a standard to another one. In that case, we have to be able to be both conservative, keeping some legacy interfaces, and also to be a little bit modern, complying with the new standard. and I will try to show you also how the new features required by the market, like security, impact also the switch specifications. So, just a few words about the standard and the semiconductor market evolution. So, if we have a look on the background, what happened on the VME and the VPX market the 20 past years, I think it's interesting to make a parallel between the time the protocol has been adopted by the IEEE committees, so the blue curve in the slide, and the real introduction in our market, the green curves. This high-level graph shows there is a time delay of 4 or 5 years between the IEEE adoptions and the introduction in the Vita standard. The reason, and there are three reasons, are really tightly connected to the market usual constraints, requirements, and practices. First is the technology time to market. We need technology in order to start a design. We need connectors, components, semiconductors, PCBs, materials. These kind of things are very important before starting a new design. Also, the standard ratification is one reason that could delay or expedite a design. We need to build the product to be interoperable, and we need specification to do that. And there is also the market maturity, because in order to start a design, we need to make sure, especially a switch, for example, in my case, we need to be sure that we will have some FPGA boards, single board computers, different kind of payload to communicate with. So that is true for the payload, but also for the switch and the system developer. I feel also interesting to come back to some bases in this presentation and to try to explain how the system uses the switches, basically. We see on the embedded market 3 types of switch and routers that I will name, for example, for the first one, the standalone switch that connects several systems via wires. Several external switch system that could be connected via wires to the Ethernet switch. We have also the inter-payload switch in a centralized architecture. This switch that could be redundant in the system interconnect all the boards together via the backplane in case of the VPX standard, for example. And there is what I call the polyvalent switch that manage both internal communications and external communication to the other system. And this slide shows an example of 2 systems that are interconnected by a fiber optical interface, the blue line, the red line, for example. But inside the system, the circles, we see different type of payload connected by via internet interface, like 1000 BX and 1000 KX. So usually inter-payload connection are performed via twist wires pair, 1000 KX, 10 giga base KR, 40 giga base KR4, and external communication and connection are performed by dual twist pair, like or fiber optical interface, like 1000 BT, 10 giga base T, or 40 giga base T. So the current embedded standard like SOSA or OpenVPX are now adopting the 10 giga and the 40 giga Ethernet and 25 giga and 100 giga Ethernet as standard Ethernet communication interface. While the 10 giga and the 40 gigabit Ethernet are already deployed in the system, new applications such radar, electronic warfare system, coming in are already requiring higher speed in Ethernet interface, and then 25 gig and 100 gig. Here it is of course not question to detail the spec of this standard, but to emphasize the features that change the way we have to address the product development. So the matrix technology, the switch technology, the first line is something that is very much important, because we have to be sure that we are using the right electronics to support the current demand on the market. We have to be sure, for example, that the matrix are properly supporting the new generation of CRDs with a comprehensive software. We are also checking that auto-negotiation is supported at that speed, and it's not really obvious, because in some speed auto-negotiation could not be supported by the matrix provider. Something new but really important, we have to make sure that the internal storing capability of the matrix are relevant to work in a burst switching on network at 25 gig multiplied by 6 or 20 interface. We have also to make sure to obtain the S parameters to address the signal integrity issues. So the signal integrity is of course something very much important. The PCB material, as Ken said before, is something that is new, but we have to be careful about the new material. Are they existing? Are they supporting the speed of the interface we would like to support on the board? The connectors, something important, but in most of the cases, the connectors are available before we start the design, as I explained before. And the power dissipation, that is something that is really complicated to address. We see that the board, even the switch, are dissipating sometimes more than 70, 80 watts. And in big system, it could be a very big issue for the customer and the integrator. So the challenge we have to address with a new generation of interface is, of course, the dissipation, as I said. So we see that there is some solution with air flow through, liquid flow through. We have also to address the signal integrity. We have to integrate new techniques for signal measurement, and we have also to be careful about the PCB material we are using for not only the switch, but I guess the payloads and the backplane. So new connectors, of course, RT3, VPX connectors are available, but customers are trying also to use fiber optical interface supporting 10 and 25 gig. So we have to be close to the connector supplier. And also we have to address something that is very much important, is the test capacities of our products. Testing a switch at the level of the Giga Ethernet is not the same thing than testing a switch at 100 Giga Ethernet. So we have to invest on new switching technologies. So, telling that, application require more processing capabilities. Processors are able to compute quicker than ever, and massive volume of data. So security is also something that is a serious topic and requires extra bandwidth. So the switch design has to follow these new requirements. The trade-off of that is the time to market. It takes more time to design the products now than before, because we have to integrate new disciplines like mechanical and thermal disciplines. We have to integrate new engineering development teams, especially in signal integrity, for example. And then there is an impact on the time to market, and of course an impact on the cost. But what is true for the board designer, I think, is true for the developer. So, just to give you some example of switches that are available on the market and are complying with the standards that and the profiles that Ken shows earlier. We have this example of the Comet 4091, that is a 3U-VPX switch supporting 10 gig and 40 gig Ethernet. That has been designed to be integrated in slot 2 of the CMOS backplane designed by Elma. It is a dual plane switch with 4 pipe on the data plane and 8 ultra-thin pipe on the control plane. Well, it is not required by the standard. We use the free connector space to integrate optionally fiber optical interface to address the requirement of the customer who would like to connect fiber interface cable to the switch directly to go outside the system, or to interconnect the boards via fiber optical interface. In the same way, we have a switch that is complying with the slot profile 3, SWH5F4U J7U, dedicated also to the CMOS backplane, slot 6. And this switch offers 5 fat pipe on the data plane, and also 4 ultra-thin pipe on the data plane, and 7 ultra-thin pipe on the control plane. And what is interesting to see in this switch is we have some fiber optical interface on the front, even for the conduction cool version of the product. And that is something that we could offer. Another example of a switch that is complying with the new SOSA profile, and that is the Comet 4520. That is a 6U dual plane switch offering 14 fat pipe and 16 ultra-thin pipe on the backplane for the data plane, and with a huge combination of various interface on the front. So here with this switch we could manage to support the 100 gigs, the 10 gigabit Ethernet, the 40 gigabit Ethernet, and also the 25 and the 100 gigabit Ethernet. So we have also the control plane that will support 15 ultra-thin pipe. So how we can help the customer to switch from an old system to a new standard? First of all, I think we have the key thing is to offer polyvalent Ethernet switch that are polyvalent but also versatile, and offering in most of the case phone connection. And for the phone connection, it's really useful to use SFP because it gives the integrator the capability to integrate the product in the way they want to, and also a huge rear variety of rear connection. 1000 BT, 10 gigabit to go outside the system, and 1000 KX, 10,000 KX for 10 gigahertz to interconnect the board together. Another example, especially for integrators who are looking for rugged environment Ethernet switches, is to integrate some fiber optical interface that can be soldered on the board. Because of course the solder transceiver can sustain much more easily the vibration and the shock, and can be qualified in a convenient way. So this is a synoptic of the switch we just see before, and we see on that switch that the product offers 32 interface. Dispatch from the back from the rear connection to the front with 2 SFP plus interfaces that are really useful to support 10 gig and even 40 gig Ethernet. an alternative also to help the customer who are not really comfortable to support to qualify their system at 10 gig, especially with the SI, the signal integrity, is to offer a fiber optical interface to make the customer able to connect the board together through this interface or to go outside the systems. And in that way, the Vita 66.5 is a very good standard. The transceiver is directly integrated on the switch, and from that point, the integrator can directly connect its wires to go to MIL 38999 connectors, for example. A good thing is also to offer to help the customer by offering polyvalent switch with multiple interface on the front and on the back. It is actually easier to do it on the VPX 6U switch. On that board, you see the Comet 4510. That is a switch supporting 40 gig Ethernet on the backplane. You see a huge variety of interface on the front, and especially a mezzanine slot that could be populated by a mezzanine customized according to an integrator-specific requirements. And this mezzanine can address different kinds of interface from, for example, the legacy 100 fiber optic 100 megabyte fiber optical interface, FX interface, for example, to the 10 gig base SX fiber optical interface. So this mezzanine offers a huge capability of customization. So this is just a view of the switch I just talked to you about. At the end, we see an increasing demand. We see increasing demand for security features like IPsec, and in that case, we see that the mezzanine available on the board, or the mezzanine slot available on the switch, can be an easy way to provide additional features like security. For example, in that mezzanine, we can easily integrate the processor to do some encryption in some Ethernet ports. So, thank you. I hope that I give you a good overview of the different trends of the switch specification we see today, and so I give you the line back to you, John.
Okay. Thank you, Frank. Now it's time to take questions from our online audience. As a reminder, you can submit questions at any time by clicking on the Ask a Question button in the presentation window. So we've got a few questions coming in. The first one, when will processor boards based on the new profiles be available? Anyone like to take that?
Yeah, this is Nigel. I'll take that as a processor board vendor. So I mentioned that there's already one vendor offering boards designed to align with the IO-centric processor profile in the market today. The compute-intensive board that we've just announced will start shipping mid-Q2 this year. And then over the course of 29, I'd expect to see a few more vendors announcing and delivering products, especially as the new profiles become ratified.
Okay. Another question. When do you anticipate the switch to 25 gig taking place? Are there products coming out this year? Are the fiber optic transceivers today good enough for rugged aircraft environments? Anyone like to take that?
Yeah, so Frank from Interface Concept. Yes, of course we see a huge requirement for this type of switch, and we are already working on the specification of the switch, on that switch today. So yeah, definitely this kind of switch, this type of switch will be available during this year, 2019, of course. And We already experimented the fiber optical interface on a rugged conduction cooled environment, minus 40, 85 degree, 5G. Of course, we have to choose this transceiver to be relevant to the environmental of the customer. But yeah, definitely we have already some experience with this type of connectors.
Okay. Is the government beginning to reference MOSA and SOSA in new contracts, to your knowledge? Anyone like to take that? Maybe Ken? Ken, did you hear that? That question? Let me repeat that. Is the government beginning to reference MOSA?
Yes, sorry, I was muted. So
That's
yeah,
right.
we're beginning to see in development hardware it being specified at very high levels. We're seeing guidance come from the secretaries of the various service branches, actually bringing attention to the contracting folks to consider these standards. And at the same time, we're seeing announcements by organizations. One, Harris posting an announcement about Mission Computer that will use modular approaches for the Mission Computer. So it is beginning to take place.
Okay, and Ken, I've got a follow-up question for that refers to at least one of your slides. There's a lot of standards, organizations, and emerging standards out there. You know, there's FACE, there's Victory, there's CMOS, MOSA, all of these things. Is there an umbrella or a dominant standard? I mean, my impression is that it's emerging that dominant standard is SOSA. Is there clear guidance from the military and from the prime systems integrators that SOSA really is the one to watch, that's the umbrella, the big dog on the block?
I would say so. I mean, you have HOST, the folks from the Navy, and the CMOS standards, the folks from the Army, collaborating with Air Force to, and then working in the Open Group Consortium, which is the group that's actually driving this, the SOSA standard, or it's hosting it, if you will. So SOSA is working quite closely with the other two. So I think the technologies that have been developed, or the standards work that's developed underneath CMOS on the Army side and then HOST on the Navy side, are being rolled into the umbrella underneath SOSA. So that sort of gives you one place to look. Now each one of them have their own needs, but there's a lot of work being done to pick up common implementation substandards where they can be used and leveraged to, I think, to try achieve as much commonality and as much reference capability as possible. So I'd say SOSA is the place to look.
Okay. As a reminder to the audience, we still have a few minutes left. If you'd like to ask a question, you can do so by clicking on the Ask a Question button in the presentation window. One that just came in is, does Interface Concept have any plans to support a 25 to 100 gigabit per second switch that will align with SOSA profiles? Frank, maybe you could take that.
Yeah. I take it. Yeah, as I said, we are on the way to offer on the market a 6U Ethernet switch that will support the 25 gig, as well as a 3U version of this switch. So I don't know which one will be available first, but this year we'll see the first 25 gig or 100 gig Ethernet switch for this standard.
Okay. I've got a question for Nigel Forrester, and that is that I believe in your presentation you were talking about SOSA, and one of the one of the things happening to help facilitate standardization is a reduction in user-defined I/O. My impression is that that's one of the biggest things about SOSA that give people pause, that people think maybe that's not the greatest thing. Can you give us an idea about the relative advantages and disadvantages of having more or less user-defined I/O?
Sorry, John, was that a question to me, Nigel? If so, can you just quickly repeat it, because I dropped off?
That's okay. It seems that one of the things that make people most nervous about SOSA is the reduction of user-defined I/O. Can you give us an idea of the relative advantages and disadvantages of reducing the amount of user-defined I/O, and what can we say to people who are concerned about it?
Yeah, sure. That's a great question. I mean, obviously, we're in the sort of a new domain here, so I guess the proof is in the pudding. But the real advantage of reducing or completely removing user I/O from many of the processor profiles is it will give you interoperability between processor boards and generations. So one thing that should enable much better and should reduce costs significantly is in technology upgrades. So we've seen many systems in the past where we've gone through 2, 3, 4 generations of processors, switches, and other functional blocks within a system. And if you can do that by literally just unplugging a board and maybe even plugging in a board from a different vendor or for an upgrade from the same vendor, that should have a significant sort of positive effect on the ability of the users to keep their systems up to date. So I think whilst there will be some perhaps learning curve as to how we reduce the number of I/O and make those systems usable, I think reality is that the benefits will outweigh the short-term pain that we'll see.
Okay. I'm going to give everybody one more chance to ask a question. We're getting to be a little past the top of the hour. So I think we have time for one more question, and that's one about costs and affordability. Some of these architectures and some of these components are complex. Are they going to be affordable? Can systems designers afford to use these new SOSA-based VPX cards and components? Who'd like to take that one?
I'll take it. I think one of the things that's being prompted by Modular Open Approach is to get the volumes up. So if there is, let's say there are less types of switches that you have to build, and built maybe to a more constrained definition, ultimately the quantities for those should go up. So we should see better use of the particular modules. So the module functionality can be extensive, it can be high performance, if you will, and that will drive a certain cost. But then there's other costs to consider. We have the cost of the module itself, volume goes up, hopefully cost goes down. And then the use of the module that can be used across, say, many different applications, then hopefully that can actually make the adaptation cost of the module be less as well.
Okay. Well, I think that's all the time that we've got left for questions. So, on behalf of Military and Aerospace Electronics, I would like to thank Ken Grobe, Director of Embedded Architectures at Elma, Nigel Forrester, Director of Business Development at Concurrent Technologies, and Frank Lefebvre, Sales Manager at Interface Concept. This presentation will be archived within 24 hours and can be accessed from the Military and Aerospace Electronics homepage at www.militaryaerospace.com. A reminder email message for the archive will be sent to registrants with a link to the archive. So we thank you for joining us today. I'm John Keller, Chief Editor of Military and Aerospace Electronics.